A WIGGY network analyzer is a device used for electrical testing and circuit analysis. It employs a unique method for sensing voltage. The WIGGY network analyzer does not draw any current when connected to alternating current mains. This is because it uses an isolated radio frequency transformer to sense the voltage across the connected load. The isolated radio frequency transformer allows the device to measure voltage without creating a direct electrical connection to the circuit under test. This isolation provides a degree of safety for the user and protects the analyzer from potential damage due to excessive current. The input impedance of the WIGGY network analyzer is effectively very high due to the isolation provided by the radio frequency transformer. A high input impedance means that the device draws very little current from the circuit it is measuring, thus minimizing any impact on the circuit's behavior. In a traditional voltage measurement, a voltmeter is connected in parallel with the circuit, and some current flows through the voltmeter's internal resistance. This current draw could affect the voltage being measured, especially in high impedance circuits. However, the WIGGY network analyzer, with its isolated radio frequency transformer, avoids this problem by inductively sensing the voltage. The radio frequency transformer consists of two coils of wire that are electrically isolated from each other but magnetically coupled. When the analyzer is connected to a circuit, the alternating current voltage in the circuit induces a voltage in a primary coil of the transformer. This induced voltage then creates a magnetic field that couples to the secondary coil of the transformer, inducing a voltage in the secondary coil. This voltage in the secondary coil is then measured by the analyzer's internal circuitry. Because there is no direct electrical connection between the primary and secondary coils, the analyzer does not draw any significant current from the circuit under test. The level of voltage is then measured via the induced current in the radio frequency transformer. The device presents what it is measuring with an accurate reading, because it is not a load on the circuit, which drastically reduces errors, which is especially helpful when analyzing very low current circuits. To understand the concept better, consider a basic transformer. A transformer works on the principle of electromagnetic induction. It consists of two or more coils of wire wound around a common core typically made of iron. When an alternating current flows through one coil, called the primary coil, it creates a fluctuating magnetic field. This magnetic field induces a voltage in the other coil called the secondary coil. The ratio of the number of turns in the primary coil to the number of turns in the secondary coil determines the voltage transformation ratio. A step-up transformer has more turns in the secondary coil than in the primary coil, resulting in a higher voltage in the secondary coil. A step-down transformer has fewer turns in the secondary coil than in the primary coil, resulting in a lower voltage in the secondary coil. In the case of the WIGGY network analyzer, the isolated radio frequency transformer is designed to efficiently transfer voltage information from the circuit under test to the analyzer's internal circuitry without drawing any significant current. The frequency of the alternating current signal also plays a role in the operation of the radio frequency transformer. The transformer is designed to operate efficiently within a specific frequency range, typically in the radio frequency range. This allows the analyzer to accurately measure voltages in circuits with high frequency signals. The design and construction of the radio frequency transformer are critical to its performance. The coils must be carefully wound to minimize losses and maximize the coupling between the coils. The core material must also be chosen to provide high permeability and low losses at the operating frequency. In addition to the radio frequency transformer, the WIGGY network analyzer also includes other circuitry for signal processing and display. This circuitry amplifies the signal from the secondary coil of the transformer, filters out noise, and converts the signal into a digital format for display on the analyzer's screen. The analyzer may also include features such as impedance measurement, frequency measurement, and waveform analysis. The WIGGY network analyzer is a versatile tool for electrical testing and circuit analysis. Its ability to measure voltage without drawing current makes it particularly useful for troubleshooting sensitive electronic circuits. It is important to note that while the WIGGY network analyzer does not draw any significant current from the circuit under test, It is still important to follow proper safety precautions when working with electrical circuits. Always ensure that the circuit is de-energized before making any connections, and use appropriate personal protective equipment, such as safety glasses and insulated gloves. The isolated radio frequency transformer is a key component of the WIGGY network analyzer, enabling it to measure voltage without affecting the circuit's behavior. This technology is widely used in other types of electronic test equipment, such as oscilloscopes and signal generators. The principles of electromagnetic induction and transformer design are fundamental to electrical engineering. Understanding these principles is essential for anyone working with electrical circuits and electronic devices. The high input impedance characteristic of the WIGGY analyzer is crucial for accurate voltage measurement in various electrical systems. Consider a scenario where you are measuring the voltage across a high resistance component in a circuit. If the measuring device has a low input impedance, it will draw a significant amount of current from the circuit, effectively altering the voltage you are trying to measure. This is because the measuring device acts as a parallel load, reducing the overall resistance of the circuit and thus affecting the voltage distribution. However, with a high input impedance device like the WIGGY analyzer, the current drawn is negligible, ensuring that the measurement accurately reflects the original voltage across the component. This is particularly important in sensitive electronic circuits where even a small amount of current draw can disrupt the circuit's operation. The WIGGY network analyzer's design addresses this challenge by employing an isolated radio frequency transformer. This transformer, as previously described, allows for voltage sensing without direct electrical connection, thereby minimizing current draw. The isolation characteristic also provides an added layer of safety, protecting the analyzer and the user from potential electrical hazards. Moreover, the use of radio frequency technology enables the analyzer to operate effectively at higher frequencies, which is essential for analyzing modern electronic circuits that often operate at high speeds. The radio frequency transformer is carefully designed to maintain its performance characteristics across a range of frequencies. This involves selecting appropriate core materials and winding configurations to minimize losses and ensure efficient energy transfer. Additionally, the analyzer incorporates sophisticated signal processing techniques to filter out noise and interference, further enhancing the accuracy and reliability of its measurements. In summary, the WIGGY network analyzer's ability to measure voltage without drawing significant current is a key advantage, making it a valuable tool for electrical testing and circuit analysis. Its high input impedance, achieved through the use of an isolated radio frequency transformer, ensures accurate and reliable measurements, especially in sensitive electronic circuits.